Welcome to the part 3 of lecture 3. In this part, we are going to discuss how to implement linear regression using Python in Google Colab. So, you have to have a Gmail account, and then in the Gmail account, if you go to the new, and here you can open a Google Colab. Here in the file, you can upload a notebook. So you can choose linear regression with mtcars.ipyn notebook. First thing you have to do, you have to upload the data from the local, and you have to upload this mtcars.csv dataset. It says remember uploads file will get deleted when this runtime is recycled. So every time you close this notebook, you have to upload the data every time. Or also, if the runtime is over or it goes into the sleep modes, you may have to upload the data again and again. So we can close this. So for this session, we are going to use NumPy, pandas, matplot, pyplot from the matplot library, scipy. From the scipy we will use the stats package. From scikit-learn we will need the linear model, and from the scikit-learn's matrix module we will use the R2. This is basically compute the R square. From the statmodels module we are going to use the API of statmodel API, formulas API. First we have to run this, then we have to run. Now it is there. If we run the data.head, it will give you the first 5 rows of the dataset. So these are the miles per gallon, cylinder, displacement, horsepower, weight. So the first thing I'm going to do, I'm going to plot the weight versus miles per gallon, because it is believed that weight has a significant effect on the miles per gallon. And we see that there is clearly a negative relationship between the weight of the car and the miles per gallon, the fuel efficiency of the car. So we are going to fit a linear model is using a sklearn or scikit-learn package, mpg equal to a plus b times weight plus error, or our standard in notation y equal to a plus bx plus error. So x, we are going to take the weight, and y as the miles per gallon, mpg. From the linear model, so this is the linear model module from the sklearn package, we are going to call the linear regression. The function linear regression, it's a built-in function. We define it as a lm, and then we fit the model lm.fit and name it as a fit underscore m1. Now we print this from there. The 37.28 is the intercept, the value of a equal to 37.28, and slope or beta is equal to negative 5.344. Now if I just write np y hat equal to intercept plus np dot, it's a dot product between x vector and the beta, that will give me all the y hats. We know a equal to 37.285 from here and b equal to negative 5.344. I ran it before, so I just wrote it down here. Now I'm defining a function called AB line. So plot a line from slope and intercept. We will provide the slope value and the intercept value, and it will draw a line. So if you run this piece, so on the x-axis we plot the weight, on the y-axis we plot the miles per gallon, and here is the fitted line using the OLS method, where intercept is equal to 37.28 and the slope is negative 5.344. Now we want to evaluate the model performance. So we want to compute the R square. So R square is 75.3%. Then we draw the scatter plot between y and y hat, the miles per gallon and the miles per gallon predicted. We see a pretty tight relationship between the actual value and the predicted value. Now so far we fit the model using scikit-learn package. Now we want to fit the same model using statmodels module or statmodels package. The advantage is the statmodels package give lot of additional information which more similar to R packages or software. So these packages, these informations are very useful, particularly from for statistical analysis. Now what is the dependent variable? Dependent variable is miles per gallon. So they have fitted the OLS method model and least square method there. They have fitted. Number of observation is 32. Number of residue, degrees of freedom of residue is 31. Model degrees of freedom 1, because you have two parameters, so 1 minus makes it. R square is 72%, adjusted R square 71.1%. Now log likelihood is negative 1 to 2.40. AIC is 246.8. BIC is 248.3. We will talk about the, so this here is the weight, the coefficient value of the weight, and standard error, and the t and the p value. So now we are going to fit the model with weight, and we are going to bring another variable, horsepower, in the analysis using scikit-learn. So we choose the weight and the horsepower here in the X and matrix or the design matrix, and in the Y our target variable is miles per gallon. So we fit the second model, model 2, and here same way we fit the model 2, and we suppose we want to prepare the new data for a prototype car. Weight is 3 ton and horsepower is 120. So the X new is 3 and 120, and beta from the new model is, we kept it in beta, and we did a prediction, and it predict that the miles per gallon, if the for the new prototype car, if the weight is 3 ton and horsepower is 120, then the predicted miles per gallon will be 21.78 miles per gallon. So we can calculate the total sum of squares of error. First we y hat compute and then subtract the y hat from the y. This is gives me the residuals, and we just square it up. So np stands for numpy. From the numpy function we calculate the square function and we compute the square error, and then we take the sum of it, then we get the total sum of square. So n is the number of samples, p is the number of features in that, so we compute that, and mean sum of squares is total sum of squares divided by n minus p minus 1. We can compute the residual standard error by taking the square root of mean sum of squares, and mean sum of residual standard error for mean sum of square residual standard error for the model is 2.593418. Now we know that miles per gallon follow a normal distribution. We are just assuming that if we follow that miles per gallon follow a normal distribution with beta naught plus beta times weight plus beta 2 horsepower comma sigma square, where residual standard error is an unbiased estimator for the sigma square. Then the lower bound and the upper bound can be for the prediction is predicted value plus minus 1.96 times residual standard error. That will give us the 95% confidence interval for the prediction. So if we run that, so this is our lower bound 16.69 and 26.86. So remember that what is our prediction if we go up little bit. So our prediction was 21.78 and 95% interval is 16.69 and 26.86. So we can say that for a prototype car, if the prototype car has weight around 3 and horsepower around 120, then predicted value will be 21.78 with a 95% interval somewhere between 16.7 and 26.9. So the interval looks little wider, but there is a room for improvement for the model by bringing more more predictors, by engineering predictors, etc, etc. Now we can evaluate the model by computing the r squared. The r squared is 82.67%, and the actual versus the predicted, if we plot to a scatter plot, it is pretty you know tightly plotted. Now let's explore the relationship between the horsepower and the miles per gallon. So if you run this, what we have is this horsepower on the x-axis and miles per gallon on the y-axis. So we can see there is a quadratic relationship between the two. So what we do is we add a new engineered variable called hp2 for hp squares. So if we run that, it is throwing a warning to us saying that this is not a good way to handling the data frame. It may give some problem. For the time being, I am just requesting you that ignore this. For the small data like this, it is working. And so horsepower for the first case, for the first sample was 110, and square of this is 12,100. In this way we now have the new x, weight, horsepower, and horsepower square. So we fit the model again, and if we do the model evaluation, Now it has gone up to 85.83%. It's even tighter. So, and if you do a model summary of that, so this is the weight, coefficient of horsepower, coefficient per horsepower square. Now all of them have a very for weight turns out to be p-value is very large. We cannot reject the null hypothesis for weight. And then if we run this thing, and then if the model for weight, horsepower, intercept plus weight plus horsepower square, if we run the model in this way, then everything is, so previously it was without intercept, so there was no intercept. As a result, the result was not very explainable. So giving, after giving the, so you have to provide the intercept and then only it will run properly. Okay, so or you have to give it in this way, so that automatically it will take the intercept model, so that you have an intercept here, and the having a correct intercept is a very important thing. So we compute the residuals y minus y hat, and looks like there is nothing much is going on, not much pattern is there. Then we did a Bruch-Pagan test for homoscedasticity, and the p-value for Lagrange multiplier statistics from the Bruch-Pagan test is 0.70, and p-value for the f value for 0.73. So we cannot reject the null hypothesis that it is homoscedasticity. We cannot reject that null hypothesis. So homoscedasticity is reasonable assumption, which is, I mean, data does not refute that assumption. Now we draw a histogram of the residuals, and we can't say really whether the residual follow normal distribution or not. We ran a Kolmogorov-Smirnov test. The p-value for the Kolmogorov-Smirnov test is 0.0515. So we can say that at 5% level of significance, we cannot really reject the null hypothesis. Remember that this mtcars data set, this is a little bit small data set with only 32 instances. So any kind of text end up with, fail to reject null hypothesis, because you don't have enough sample size, enough statistical power. So because of that, it will end up rejecting the end up not failing to reject the null hypothesis. So um, in the next hands-on exercise, we will consider a slightly moderately sized large dataset, and we will explore even more and more other aspects of the linear regressions, like multicollinearity and the variable selection and etc. I start this analysis or the hands-on only with the small data set, so that just to motivate you with the Python and the environment of the Python. But we will do more and more hands-on in this regard. Thank you very much. Please keep watching.